Welcome to the deep dive. Today we're going deep on photons.
Oh, yeah.
You know those tiny particles that make up light?
Right.
But there's so much more to them than meets the eye.
Oh, absolutely.
And for this deep dive, we've got a really cool source.
Oh.
A whole conversation with an AI chatbot.
Okay.
All about photons.
Oh.
It goes deep, covering the basics all the way to quantum weirdness.
Oh, wow.
So if you've ever wondered what light really is or how it shapes the universe, you're in the right place.
I love it.
I think what's so fascinating about this AI conversation is just how much is packed into this seemingly simple concept of a photon.
Yeah.
It's like a doorway to understanding everything from why the sky is blue to, the mind-bending mysteries of the quantum realm.
Right.
So let's start with Photons 101.
Okay.
What exactly is a photon?
Wow.
I get that they make up light, but what does that even mean?
So think of a photon as the smallest possible piece of light.
Okay.
Like a tiny packet of energy. It's the fundamental particle of light and all forms of electromagnetic radiation. Everything from radio waves to gamma rays.
So those radio waves coming from my favorite station are made of photons.
Exactly.
The X-rays they use at the dentist, those are photons too.
It's all photons, just with different energies.
Wow.
And here's something that always blows my mind. Photons have no mass.
No mass.
Yeah.
But if they don't weigh anything, how can they carry energy?
Right.
That doesn't seem to make sense.
It's one of those things that really challenges our everyday intuition.
Okay.
In the world of photons, energy and momentum aren't tied to mass in the way we're used to.
Yeah.
They're pure energy zipping around at the speed of light,
Wow.
interacting with matter and causing all sorts of fascinating phenomena.
So you're saying these massless photons are zipping around carrying energy? But what about this whole wave-particle duality thing?
Yeah.
That's what really gets me.
It is a head-scratcher.
So a photon is like a tiny bullet of light and a wave.
Yeah.
How is that even possible?
It's one of the biggest head-scratchers in physics.
Oh.
Think of the classic double-slit experiment.
Okay.
You shine a beam of light through two tiny slits. Now, if light were just particles, you'd expect to see two bright lines on the other side.
Yeah, like two little beams of light shining through.
Exactly. But that's not what happens.
Well,
Instead, you get a pattern of bright and dark bands, an interference pattern, just like you'd see with waves in water. It's as if each photon is somehow going through both slits at the same time and interfering with itself.
wait, so it's like the photon is a wave until it hits the screen and then suddenly it decides to be a particle.
Well, it's a bit more complicated than that.
Okay.
But the key point is that photons can exhibit both wave-like and particle-like behavior,
Okay.
depending on how we observe them.
Interesting.
And that duality is the foundation for so much of how photons interact with the world.
So they're like tiny little chameleons of the physics world,
Yeah.
changing their behavior depending on who's looking.
That's a great way to put it. And this shapes how they interact with matter.
Okay.
Our AI chatbot outlined three main ways: absorption, emission, and scattering.
Okay, let's break those down.
Okay.
What exactly happens when a photon is absorbed?
So imagine a photon hitting an atom.
Yeah.
When a photon is absorbed, its energy is transferred to an electron in that atom, bumping it up to a higher energy level.
So it's like the atom is eating the photon
Yeah,
and getting a little boost of energy.
exactly.
I like that analogy.
Yeah.
And what about emission?
Emission.
Is that like the opposite?
Exactly. When an electron in an excited atom drops back down to a lower energy level, it releases a photon.
So it's like the atom is burping out a bit of light.
Uh-huh. Yeah.
I like that.
Yeah.
Okay, so absorption, photon in atom gets energized.
Yeah.
Emission, electron goes down an energy level, photon out.
Right.
What about scattering?
Scattering.
That sounds more chaotic.
Scattering is when a photon bounces off an atom or molecule, sometimes changing direction but not losing energy.
Oh.
Think of sunlight hitting the atmosphere.
Okay.
The reason the sky looks blue is because of something called Rayleigh scattering. Blue light scatters more than other colors,
Oh.
so we see that beautiful blue hue overhead.
So it's all these tiny photons bouncing off air molecules that create the colors of the sunset too?
It is.
That's amazing.
And scattering isn't just about pretty colors.
Yeah.
It's also crucial in many technologies like radar and medical imaging.
Now, I know we've barely scratched the surface of the photon world.
Right.
And I'm already feeling like my brain needs a break.
Take it easy.
But before we do that, I have to ask, things get even weirder when we talk about quantum entanglement, right?
Oh, absolutely. This spooky connection between photons isn't just theoretical. It's the foundation for mind-blowing ideas like teleportation.
Oh, wow.
But we'll dive into that rabbit hole after a quick break.
All right, so we're back and ready to ready to get into entanglement.
Okay.
Two photons linked across space. It sounds like something out of Star Trek.
It does, doesn't it?
Yeah.
But quantum entanglement is a real phenomenon.
Wow.
And it's one of the strangest things in all of physics.
Okay.
Basically, you have two photons that are linked in a way that even if they're separated by vast distances, they still act like they're connected.
So what does that even mean in practice?
Right.
Like if I measure something about one of these entangled photons, what happens to the other one?
That's the wild part.
Okay.
When you measure the state of one entangled photon, say its polarization, the other photon instantly takes on the opposite state.
Whoa.
No matter how far apart they are.
So they're like psychic photons,
Huh?
sending secret messages across the universe.
It's tempting to think of it that way, but it's not quite like that.
Okay.
Entanglement doesn't allow for faster-than-light communication in the traditional sense,
Okay.
but it does point to a deep interconnectedness in the quantum world,
Right.
where things are linked in ways we're only just beginning to understand.
You mentioned teleportation.
Yes.
Is this spooky action at a distance how we're going to be beaming ourselves up to spaceships someday?
Not quite. Quantum teleportation is a real thing, but it's not about moving matter. It's about transferring information.
Okay.
Think of it this way. You can use entanglement to instantly transfer the state of one photon to another photon, even if they're far apart.
So we're not teleporting Captain Kirk yet,
Right.
but maybe we're teleporting information.
Yeah.
That's still pretty wild.
Absolutely. And it has huge implications for things like secure communication.
Oh, okay.
Imagine a world where it's physically impossible for anyone to eavesdrop on your messages, because any attempt to intercept the information would disrupt the entanglement and be instantly detectable.
Oh, wow.
That's the promise of quantum key distribution, or QKD.
Unhackable communication.
Yeah.
Thanks to the weirdness of quantum mechanics.
Exactly.
I like it. Okay, so our AI source also mentioned that photons are key to all sorts of technologies that are already shaping our world,
Yeah,
not just the futuristic stuff.
that's right. Photons are already at work in countless ways,
Right.
from everyday devices to cutting-edge scientific instruments.
Like what?
Take fiber optic communication, for example.
Okay.
Those cables that carry internet data around the world at lightning speed,
Right?
they work by transmitting pulses of light photons through thin strands of glass.
So every time I watch a cat video online, it's photons delivering the cuteness. Amazing.
Exactly. And then there's LiDAR,
LiDAR.
which uses lasers, beams of concentrated photons to measure distances with incredible precision.
Okay.
It's used in everything from self-driving cars to mapping the Earth's surface.
So a self-driving car is basically shooting out photons and using the reflections to see the world around it.
That's the basic idea.
Cool.
And because photons travel at the speed of light, LiDAR can create incredibly detailed 3D maps in real time.
Yeah.
It's revolutionizing fields like archaeology, allowing researchers to see through dense vegetation and discover hidden structures.
So photons are like the ultimate multitaskers of the physics world.
Yeah.
They bring us cat videos, help cars drive themselves, and even reveal ancient ruins.
And that's just scratching the surface.
Oh, wow.
There are so many other exciting applications of photonics, the science of light.
Right.
Our AI source mentioned optical coherence tomography, or OCT.
OCT, what's that all about?
OCT is a non-invasive imaging technique that uses light to create high-resolution images of biological tissues. It's like an ultrasound,
Okay.
but with light instead of sound waves.
Interesting.
It's particularly useful in ophthalmology, allowing doctors to examine the retina and diagnose eye conditions without any surgery.
So it's like giving your eye a super detailed photo shoot,
Yeah.
all thanks to photons.
Exactly. And then there's SPINCT, which uses gamma photons, a very high-energy type of light, to create 3D images of the body's internal structures.
Okay.
It's incredibly useful in medical imaging,
Yeah.
helping doctors diagnose and monitor conditions like heart disease and cancer.
It's amazing to think that something as simple as light can be harnessed in so many ways,
It really is.
from communication to medicine and beyond.
Absolutely.
But our AI friend also hinted that photons could hold the key to some truly futuristic technologies.
Absolutely. As we delve deeper into the quantum realm, we're discovering new ways to manipulate and control photons,
Right.
leading to all sorts of mind-boggling possibilities.
Like what? Give me an example.
One area that's particularly exciting is photonic integrated circuits, or PICs.
PICs. Sounds intriguing.
The idea is to shrink down all the components of a complex optical system lasers, lenses, detectors, and so on, onto a tiny chip, just like we've done with electronics.
So instead of having bulky lasers and lenses taking up tons of space,
Yeah.
you could have everything packed onto a tiny chip.
Exactly. Imagine the possibilities: smaller, faster, more efficient optical devices that could revolutionize everything from telecommunications to computing.
I'm trying to picture a computer that runs on light instead of electricity.
It's not as far-fetched as it sounds.
Wow.
And then there are metamaterials.
Instead of materials.
These are artificially engineered materials that can manipulate light in ways that are impossible with natural materials.
Wait, you're saying we can engineer materials that bend light in ways that nature never intended?
Yeah.
What kind of sorcery is this?
Haha, it's not sorcery, it's science.
Okay.
And it's leading to some truly mind-bending applications, like superlenses that can resolve details smaller than the wavelength of light.
Wow.
And even invisibility cloaks that can bend light around an object.
Invisibility cloaks. Now you're definitely messing with me.
Haha, I promise it's real science. It's still early days, but the potential of metamaterials is enormous. Who knows, maybe someday we'll all be walking around wearing invisibility cloaks thanks to the power of photons.
I'm not sure I'm ready for an invisible world just yet.
Uh-huh.
But it's clear that photonics is not only shaping our present, but also paving the way for a future filled with incredible possibilities.
Absolutely. But before we get too carried away with futuristic visions, we need to circle back to some fundamental mysteries about photons that still haven't been solved.
Yeah.
These puzzles could hold the key to unlocking even deeper secrets about the nature of the universe.
Well, we've talked about the waves-particle duality.
Yeah.
But are there other mysteries surrounding these tiny particles of light?
Well, one of the biggest mysteries is the wave function collapse.
Okay.
Remember how we talked about photons existing in this weird superposition of states?
Yeah.
Like being both a wave and a particle?
It still makes my head spin.
Well, when we measure a photon, its wave function collapses. It goes from being in this blurry, uncertain state to a definite state.
Okay.
But how and why that happens is still one of the biggest unanswered questions in quantum mechanics.
So it's like the act of observing forces the photon to choose a specific state.
Yeah.
Like it's been caught in the act of being both things at once and has to pick a side.
That's a good way to think about it.
Wow.
And it raises profound questions about the role of the observer in quantum mechanics. Does our observation create reality, or are we simply revealing a reality that was already there?
Wow.
These are questions that philosophers and physicists have been debating for decades.
So photons are not only the building blocks of light, but also the source of some serious philosophical head-scratching. I'm ready to dive deeper into these mysteries, but I think my brain needs a little recharge first. We'll be back in a flash to tackle the final leg of our photon-powered journey. Okay, we're back, and I am ready to tackle the universe.
All right.
Our AI source hinted that photons play a huge role in our understanding of the cosmos.
They do. These tiny particles, they carry information across vast stretches of space and time, giving us glimpses into the universe's history and even the workings of gravity itself.
So how far back are we talking? Can photons really tell us about the early universe?
Absolutely. Our AI friend mentioned something called the photon epoch.
Photon epoch.
Yeah, it sounds like a sci-fi movie.
Yeah, it does.
But it refers to a very real period in the early universe, just a fraction of a second after the Big Bang. Back then, the universe was so hot and dense that it was essentially a sea of photons.
So we're talking about photons that have been around since practically the beginning of time.
Exactly. And as the universe expanded and cooled, these photons eventually became what we observe today as the cosmic microwave background radiation,
Okay.
a faint afterglow of the Big Bang that permeates all of space.
So by studying this cosmic microwave background,
Right.
scientists can learn about the conditions in the very early universe.
Yeah, it's like looking back in time with a giant photon telescope.
That's amazing.
And it gets even wilder.
Right.
Our AI source also mentions something called a photon sphere.
Photon sphere.
Have you ever wondered what happens to light near a black hole?
Well, I know black holes are supposed to be these cosmic vacuum cleaners that suck up everything, including light.
Right.
So I'm guessing it doesn't end well for the photons?
That's partly true. Black holes have such strong gravity that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. But just outside that event horizon is this fascinating region called the photon sphere.
So what happens in the photon sphere? Do the photons just hang out there?
Not quite. In the photon sphere, gravity is so intense That it bends the paths of photons so much that they essentially get trapped in orbit around the black hole.
What?
Imagine light going in circles.
Instead of falling into the black hole, the photons are stuck in this cosmic merry-go-round.
It's a bizarre concept, isn't it? But this bending of light by gravity is what leads to some truly amazing phenomena.
Okay.
Like gravitational lensing.
Gravitational lensing is that like when light gets bent around a massive object, kind of like a magnifying glass?
Exactly. Imagine a distant galaxy behind a massive cluster of galaxies.
Okay.
The gravity from that cluster can act like a lens. Bending and distorting the light from the background galaxy, it can even create multiple images of the same galaxy.
Wow. So black holes and galaxy clusters are like nature's giant telescopes warping space-time and letting us see things that would otherwise be hidden. That's incredible. It makes you wonder what other secrets are out there waiting to be revealed by photons.
There are undoubtedly countless mysteries still to unravel, but one thing is clear. Photons are much more than just particles of light.
Yeah.
They are messengers from the cosmos, carrying stories of distant stars, black holes, and even the universe's earliest moments.
It's humbling to think that something so tiny and seemingly simple can hold such profound secrets. And it makes me wonder what other surprises are hidden within the realm of photons. What new discoveries and technologies await us as we continue to explore the nature of light.
Those are questions that scientists are actively working to answer.
Right.
Every new experiment, every observation of a distant star or galaxy brings us closer to understanding the full potential of these fascinating particles.
Well, this has been an incredible journey. From the basics of light and color to the mind-bending world of quantum mechanics and the vastness of the cosmos, photons have proven to be far more complex and fascinating than I ever imagined.
And that's the beauty of science. The more we learn, the more we realize how much more there is to discover.
So to our listeners, we encourage you to keep exploring, keep asking questions, and keep that sense of wonder alive. After all, the universe is full of photons, just waiting to tell their stories to those who are willing to listen.